un Romain, Sansica, une thèse à Southampton sur l'interaction choc-couche-humide. Tu es venu chez nous pour travailler avec le CNES, notamment sur les instabilités de tudière. C'était en 2015, 2016. 2016. Voilà. Et ensuite, tu es parti au Japon. Et là, je ne sais pas ce que tu as fait, et donc c'est vraiment une bonne chose que tu sois là pour expliquer. Merci André.
Thank you for inviting me. Thank you for being here. Yes, so the idea today is to give you a little bit of an overview of the activities that we are doing at JAXA, mostly with focus on digital transformation and CBA or certification by analysis. I will give a little bit of an idea of what both experimental and numerical activities are, with specific focus on transonic buffet and stall. So there's only me here, but this is the work of many people that I'm happy to acknowledge later. And yes, I want to give you a little bit of motivation why we are trying to do digital transformation and certification by analysis. I will rapid overview of activities on stall and transonic buffet, but given that yes, some of the methods that I'm using have been started here, I want to focus a little bit on GSA, global stability analysis, based transonic buffet prediction. And then a little bit of advertisement for upcoming events and workshops. So, aircraft lifecycle digital transformation. This is part of the Aviation Technology Directorate. We are located in Shofu. So, if you know Tokyo a little bit, this is Shinjuku and Shibuya, where you go out partying, let's say. We are 15 minutes by train and short bus ride. The center is quite nice. We also have an exhibition hall. So I put this because somebody might come in September. So to give you a little bit of an idea where we are located. We are the largest cluster of wind tunnels in Japan. We have many test facilities, aero engine facilities, a lot of wind tunnels of different sizes and different speed ranges. And notably the transonic one is the one that we use for the buffet experiments. We have flight test aircraft, helicopter, flight simulator that are all part of also digital transformation. We have the supercomputer called JSS3. So if you know Fugaku, Fugaku until a couple of years ago before Frontier was the most powerful supercomputer, and JSS3 is the same architecture, it's based. When it became operative in 2020 was ranked 19, so it is still powerful. But next year we're gonna change it. So we are trying also to move towards GPU. This one is almost fully CPU. So yeah, we have big projects that I summarized this way. The one that I'm not going to explain all, but the one that most of my activities come from is this SkyDX. So the objective is to drive digital transformation for the entire aircraft lifecycle. What we mean with digitalizing the aircraft lifecycle. So we have 5 phases, roughly, in the aircraft lifecycle, from design, certification, production, operation and maintenance, and disposal. And the objective is to create and provide simulation tools that aim at reducing and not replacing physical testing. So if we create so-called digital twin from each of these phases. We want to do simulations and testing on the virtual model that is going to be much cheaper and quicker. Yes, but today, so there are many projects, and I am mostly involved in the certification by analysis part, so this is what I'm going to talk about today. Sorry. So, yes, the motivation is that now, so in this table, from older to newer aircraft, you can see development time and costs have increased significantly. And in the specific certification can take a big bunch of this development time and costs. Often during certification, so during flight testing, we find some issues that require redesign and then cause delays. The systems are becoming more and more complex. It's very difficult to introduce new technologies. So CBA targets these problems, and yeah, the idea is we want to reduce time and costs. So certification by analysis. Currently, the use of CFD in industry is represented here. This is flight envelope, let's say, loads versus airspeed. So this region we are at takeoff, cruise, and landing. And the region where CFD is well calibrated is very small. Usually it's limited to runs. And CFD is not regulated in the sense that we cannot use it to certify a plane. So we have two streams of research activities at JAXA. The first one is trying to regulate the CFD for those regions where CFD is working well. And the second part is trying to extend CFD to the whole flight envelope. For the regulation of the well-calibrated CFD, we have created recently this project called ChainX. It's coordinated by JAXA and partnered with the major industries like Mitsubishi, Kawasaki, Subaru. And the interesting thing, there is also the Japanese certification authority, because we want to propose standards and regulations for numerical simulations. And at the end of this project, we are also we will also have like a simulated certification review. So we want to put everything in place so that numerical simulations can be used for certification. But that one is a bit more documentation-based, administration-based, regulation-based, and not so research-related, let's say. Extending the flight envelope is what research activities actually aim at. How we want to achieve this extension to the whole flight envelope is by increasing access to HPC and use modern solvers with modern architectures. We want to move from only runs to a little bit higher fidelity methods, and not only use them for design, but also for certification. So yes, hybrid runs LES, wall models LES, improving runs modeling with AI. And everything related to geometry modeling, adaptive mesh refinement, and so on. Another important thing that needs to be done for certification is uncertainty quantification. So this is something we just started, we're very new, and to the experts. And then, of course, if you want to use CFD, you need to have experiments to validate against. And there's not a lot of experiments for critical phases, like at the edge of the envelope, where you have unsteadiness like buffet, or when you have stall. So again, for the sake of this presentation, I will focus mostly on these two configurations, low speed stall and transonic buffet. So let's start with the experiments. It's been more than a decade now that in this transonic wind tunnel is a 2x2, I should say 2 meters by 2 meters, because if you talk to the Americans, they think it's 2 foot by foot meters. So it's relatively big. We have the NASA CRM model, that is one of those that we use for many experiments aimed at opening data. And in the years, measurements have been accumulated, measurement techniques have evolved, and we started from simply getting aerodynamic forces to now having unsteady PSP or high resolution steady PSP. We provide this data for this is a domestic aerodynamic prediction challenge. So it's pressure sensitive paint. And so we provide experimental, this is like a high lift prediction workshop or drug prediction workshop. We provide data, it's domestic, but everybody performs the same simulations. And since last year, I had to organize this, and I decided to move from Buffett to Stoll because most of our activities are actually on Stoll. So it's been a big change because in the previous editions was on Buffett. And also, so far, this has been mostly used domestically within Japan, but I'm now part of the committee for the DPW, and the idea is that we provide the experiments for this much larger workshop to compare against. The other experimental activities are Stoll. This is another wind tunnel that we have. It's a little bit bigger, but it's low speed. We are currently manufacturing this model. It's a half span, 8% scaled CRM high lift. So high lift accounts for the presence of slats, flaps. We also have nacelle. And we are part of this NASA CRM high lift ecosystem. Maybe it's not very clear, but in 2025, we will do experiments, and again, we will open data for everyone, so that prediction workshops, they can be used in prediction workshops, and also as part of some collaborations that we have with trilateral collaborations with DLR and ONERA on CL Max. But yeah, let's move towards numerical tools. Very, very rough grouping of different types of simulations. For CBA, if we want to have a little bit more accuracy, we probably would target multi-fidelity physics solving tools. It takes longer, but yeah, it depends on what you need to do. And these are some of the methods and approaches that we are using or developing. And this is opposed to what it would be data-based rapid modeling, so very quick answers up to, let's say, real time, that would be used for different phases of the aircraft, where you need very quickly some answers. And we go from reduced order modeling, model-based, AI-based, and system identification that we did, which is a couple of years ago. But yes, for the sake of time, I want to focus, of course, on stability. I guess it's of interest, and a little bit on higher fidelity simulations. So starting with high fidelity simulations, this is the work that David Lasher did. So he used to be a fellow got fellowship from the government. So technically he was in JAXA, but for the last couple of years, he took OpenSBLI, that is code he developed during his PhD, and he extended the capabilities of this code to target Buffett. Now he has been hired at JAXA, and we want to do a similar thing, but for finite volume of structured grids and so I imagine you know how these kind of things work, but I will explain it very quickly. We have the user specifying governing equations. As long as you can write it in index notation, in theory you could solve any equations. And of course, you will specify input parameters, boundary conditions. Of course, you can choose anything. There are some library, some availability. But the code, the framework David developed, it's taking these equations and automatically getting C code. At this point, the C code is sequential, and it's given to this domain-specific language library that is called OPS. It's developed in Oxford, and it's for structured grids. And you can select which target machine you need, and it will automatically parallelize your C code. And since these libraries are developed by software engineers that really know what they're doing, so usually they're optimized for the target machine. And then once you get the code, you just have to run it and get your results. Some of the simulations we could do with this tool, so I call it implicit alias, meaning we don't have subgrid scale models, but we just let the grid unresolved to introduce some dissipation, or we also went up to DNS. But we did calculations of up to 10 million points, so very large simulations on a relatively small number of GPUs. And we looked at different sensitivities, at the appearance, intermittent appearance of these buffered cells. So these were relatively simple geometries. It's just an airfoil extruded with periodic boundary conditions. But yes, for CBA, as well as trying to understand more in detail about the mechanisms, we also use these large databases for model training. In terms of outreach, we are writing some stuff. So David won this award last year for this work he did, but now we are more focused on publishing. Some are already under review, some in preparation. We plan to present, if accepted, some of this work at IUTM Transition. But yes, soon, hopefully, this version of OpenSBLI will be released, and it's open source, so it can be used by anybody who has resources, let's say. Moving to stability, most the talk will be about this. Now, I guess I don't have to explain you what global stability is, but just for sake of completeness, I will go quickly through it. We won't use it because for certain type of phenomena, like if we want to predict transonic buffered onset in the specific, if we do stability, or if we do more classical simulations like unsteady runs, stability can give you a very large computational saving, especially if we are close to the onset, where these simulations will take a very long time before they settle and before you understand whether the case is steady or unsteady. GSA can be pretty useful in these cases. It is 3D stability calculation. We don't make any homogeneous direction assumptions, so the flow can vary in all direction. We can deal with very complex geometries like a full aircraft. This opposed to local or bilocal, where you assume 2 or 1, and not that these are bad, of course, but if you want to do full aircraft, of course, you cannot assume homogeneous directions. Yes, the framework is relatively classical stability framework. I know you know all these things, so I'll skip a little bit. But we have 3 main challenges when we do stability. First one is calculating the base flow. Phyllis will be happy about this, but in the runs based GSA framework, the base flow corresponds to the runs solution. So I simply use our legacy code, some structured finite volume code that is faster. And the other challenge is deriving and implementing the linearized solver. I will explain a little bit in the next few slides, but basically we need a linearized Durand solver called faster GSA. And then solving this eigenvalue problem, this L matrix is discrete linearized Jacobian, so the size is number of degrees of freedom times number of degrees of freedom, so it's very huge, and we need to solve it in a RAM-efficient way. So what we did is what I was doing here, it's time stepper, and I know this, or what I call like Jacobian-free system reduction, and you solve the eigenvalue problem on a much smaller matrix. We recently published this paper where everything is well explained, I hope. But of course, we will discuss about this a little bit more in detail. So about linearization and eigenvalue problem, because something a little bit different from what I was doing here. So this is a schematic representation of what time integration would be for unsteady calculation. We start from a given initial solution, and then we start integrating in time, and for each time instance, even delta t, we will advance our solution in time. So this is like a simple time integration that you would do for a Urans in a Urans code. For the stability, so what I did was, so the initial solution would be your base flow plus your perturbations that are pre-multiplied by this amplitude epsilon. And then I don't actually linearize the routines, but I start advancing the nonlinear solver up to a certain delta t of Krylov. So after n delta t, delta small t. And then I do a Taylor series expansion truncated to the first order, and I calculate after orthonormalizing. I populate my Krylov base, I populate my Hessenberg matrix, and what I get is the perturbations for the next iteration. Then I put that here and I restart this. Once I'm satisfied with the size of my Krylov base, I perform the eigenvalue problem on the Hessenberg matrix that is very small, and of course obtain spectrum and project the noise. So the linearization part is something different with respect to what I was doing here, where I was actually linearizing every routine. This next slide, I tried to list pros and cons, but yes, this is a bit different from what was done here. This part is exactly the same, but it's important because it's the enabler for doing GSA on very large grids. We don't have to extract the Jacobian, like for example, it's done in OIRA, and we can do it therefore on very large grids. And you will see in a few minutes on what kind of grids we did it. So pros and cons, rough list. So with this linearization technique, we don't need to linearize any routines. So it's very useful if in your, for example, turbulence model, you have step functions, and you need to regularize anything. And as a matter of fact, you don't have to linearize anything. So you can simply use your code and use all the features that your code has. So you can do sensitivity studies and so on. Excluding the discussion about what the base flow could be, this could also be applied to higher fidelity methods. And as I said, we can deal with large 3D grids. The cons side, the base flow must converge very, very well. If it's not machine precision, if it saturates at a certain level, you will start having spurious modes, usually steady and physical spurious modes. You have to deal somehow with those. But yeah, it's very important to converge well the base flow. The delta T of Krylov cannot be too large. We are actually running a nonlinear solver, so the nonlinearities, if they grow, then your stability simulation is invalid. And the other important thing is this amplitude that we use to multiply equations with. And there's still some work to be done for sure, but for the moment I define it locally. It's different values for the mean flow and turbulent quantities. And yes, when the base flow is not converged, I still have problems when in the presence of turbulent flows. So at the moment, what I'm doing is perturbing the turbulent quantities, but not including them in the trade-off base. There are some issues with this. We can discuss later about this. It's a little bit, I have some slides, but the idea is that in this way, it's very robust and not bad, as you can see. This is a little bit of a roadmap. Of course, I started from the compressible cylinder wake to start testing, and then some validation against literature for the airfoil transonic. First 3D configuration I did was this swept wing with sidewalls that comes from some experiments at JAXA. Was not very successful. I will show you why. But yes, probably the most interesting thing that I will focus on is the full aircraft for transonic buffet. And then recently we moved to stall, so I started again validating 2D. This is work on ERA with Frederick. And I will show you a little bit what GSA gave me for the full aircraft high lift configuration and low speed stall. So the validation, I'm not showing anything. I have some backup slides. I promise you it was validated, but I can show you later. For the first 3D case, yes. So here we have, this is a PSP, so pressure sensitive paint based DMD mode, and coming from some experiments at JAXA in a smaller wind tunnel, transonic wind tunnel always. We had swept angle, and this is one of the modes that I was getting. Resembles what we have here. There is a competition between the cross-flow component, because we have a swept wing, and a cross-flow component that is given by the presence. Here we would have large corner separations. So there is a competition, and sometimes you also see inboard traveling waves. That's quite interesting. But yes, the runs was over predicting the corner separations. So of course, if your base flow is not good, your stability automatically will not be good. So this is a study that should be improved at some point. But when we did it for the full aircraft transonic buffet condition, so previously the grid here, we started having relatively big grids for runs, 20 millions. But here we started moving to a little bit bigger, and this is something already that if you want to extract the full Jacobian, it will be quite difficult. But I will explain a little bit in detail about this later. This is very new things that I presented last January at SciTech. So low speed, we picked an angle close to CL max, and the grid now is significantly bigger. We have 200 million cells. And the interesting thing was inside the nacelle we had separation, and from here there was this mode being generated. But once it exits the nacelle, it's deflected upwards, hits the wings and flaps, so potentially contributes to lows. Yes, the nacelle is empty, but because it's on the experiments in real life, there will be an engine. But if you do experiments in a wind tunnel and you want to compare your CFD with, you must know about this phenomenon. But now, yes, the bigger part, hopefully I'm not too late. So about transonic buffet on set prediction. The flow conditions have been based on two sets of experiments. First one from experiments available at JAXA. Reynolds number is I call the wind tunnel Reynolds number. So it's about 3 million, 2 million, 2.3 million. But then I also tested it on flight Reynolds number conditions. It was not a flight test, it was still in wind tunnel, but in NTF and NASA, where they can go up to 20 million Reynolds number. Yes, always these two, faster and faster GSA, respectively, the base flow and the stability calculation. The geometry is the CRM body wing. Actually, there's also tail, so this is wrong. But we considered experimentally measured wing deformation. So it's rigid wing, it's not fluid structure interaction here, but we considered the fact that the wing is deflecting. And yes, we tried a bunch of different grids and results here for the finest that we got from transonic buffer. That is about 164 millions. Of course, first thing to do is to make sure that your base flows, in this case the RANS solutions, are of good quality. So we compared against available experimental data. In this case, you see CP distributions at different wing sections. And the agreement, this is for a low angle of attack. And for a higher angle of attack, of course, there are some differences. Notably, sometimes we don't capture the right location of the shock. But this is a very high angle of attack. Also for a smaller one, we have some differences, but in general, they are good solutions. In terms of aerodynamic forces for lift, drag, and momentum, so the red circles, they correspond to the results that we got. So these are in very good agreement with some other contributions from participants from the prediction workshops. So this shift, it's not something that we only had. And as a matter of fact, in these workshops, we decided, let's do an arbitrary shift with the idea that this groups all the experimental unknowns. And when you apply the shift, things start matching very well. But of course, it's a bit of an arbitrary shift. Looking at the solutions, so if we look at the CL alpha curve, this is what we have for different angles of attack. For each angle of attack, we have a base flow, and for each angle of attack and base flow, we did stability. But it was interesting, I think, to identify roughly 4 solution branches. The first one here, where we have a very linear trend of lift with angle of attack. If we look at main wing, and this one, here's the junction between fuselage and wing. So this is important junction where usually you have side of body separation. But for this first branch, we have fully attached flow. For this second branch, where we start seeing the lift, not following the linear trend anymore, we start having separation on the main wing. For this other branch, we start having this side of body separation. And in the fourth branch, there's a significant drop in CL, where it's caused by this side of body separation that becomes very large. So for all these cases, we did stability. And so this is growth rate and frequency versus angle of attack. So when the growth rate becomes positive, we will have unstable base flow, and we will have buffet on, let's say. The light blue line is the experimental onset angle of attack that was measured with strain gauge on the wing. So after a certain level of vibration, they considered buffet onset. And as you can see, the one predicted by GSA was pretty good. Once we move far from the onset, as you know, things start being a bit different because the base flow and the mean flow, they change significantly. But if we are near the onset, what we found was one unstable mode, And the models, the GSA model is here represented and compared to some available, so this would be pressure fluctuations from the unsteady PSP. And it was nice. Of course, the comparison is not super fair, but it was nice to see that it was very similar. And three-dimensionally, this mode is very close to what Sebastian team in Liverpool found and concerns this appearance of Buffett cells. But what we did was moving a bit forward and also for moving far away from the onset, we started having multiple modes appearing, and compared to spectra from PSP and Q-Light, they were in similar range. This one is the mode that was existing also at so close to the onset that also Professor Tim found. What we found interesting was this mode, whose Strual number is very close to the Strual number of 2D Buffett on 2D airfoils. And I call it quasi-2D because it might be still Buffett cells, but now they have a very long wavelength. So I was speculating that this is what 2D Buffett would be for a 3D configuration. And then since we had side-body separation in this body-wing junction, there was also another mode here that was generated. And the interesting thing is that these modes, they actually hit the tail as well. So yeah, it can be interesting from a load point of view. And yes, so these results are for the wind tunnel Reynolds number case, but very similar things I found them for flight Reynolds number case. So I just show this. Yeah, actually, that's it. A little bit of advertisement, I would say. So in Japan this year we will have 2 big conferences. First ICCFD that Paula is organizing in Kobe in July. Paula will come to JAXA after that, so we're very excited for a seminar. And then there will be a U-turn transition in September in Nagano. So I took this chance to still trying to organize a mini workshop focused on Buffett. It's like some sort of second edition of what was organized a couple of years ago by Professor Tim and Professor Sandam at Liverpool and Southampton universities. We fixed the date. UGC has been helping also with the organization of this. We agreed on doing it just before U-turn. So there's the opportunity for people to come in person. And yeah, I'm trying to organize a little bit of a visit at JAXA and as well as the workshop. So if you are interested, if you're going to a U-turn, but if you're interested, the event will be hybrid, so it can be also followed online. And if you're not Buffett specialist, but you still want to join, you're more than welcome. It's not going to be, it's going to be just presenting, sharing latest publications. The topics that we selected are these three. So we want to focus on the difference between 2D and 3D Buffett. Also, laminar Buffett is becoming more and more relevant. So we want to address differences between turbulent and laminar Buffett. And of course, there's a lot of work on data-driven modeling and control. And again, if you are interested in Buffett, now I'm helping here with this drug prediction workshop that will be held in 2026 at AIAA Aviation. It's maybe in San Diego, I don't remember, but it was in the US. And we have different technology working groups, we call them. One of them is going to be on unsteady aerodynamics and Buffett. and I'm coordinating this with Brent Pomeroy at NASA and Daniela Rabet at Technion, Israel. And yeah, as I mentioned, the idea is that the JAXA dataset that we have, it's very rich. We would like to use it as a benchmark solution for the test cases. There's a lot of work going on because this is a joint workshop with the aeroelastic prediction workshops. So some cases will actually be unsteady CFD and flexible wings, so things start becoming very complicated. Yeah, these types of workshops, they try to push the limits or at least assess state of current state, how do you say, up-to-date state-of-the-art solvers. And with this, I conclude. I thank you again for being here, for having me back and Fluid, and I'll be happy to take any questions.
I'm quite impressed by the level of food simulation. But I'm also curious about the time. How long does it take, for example, the development, processing, the match, etc., process, and then post-processing? Relatively, what is the most costly